Hey all! So today we're going to talk about writing statements in what's called symbolic logic. So we're going to be using symbols like this, some of which you've seen before maybe, to write out the statements and also to interpret statements written in symbolic logic. You might think, oh, the notes look a little bit different. They do. These videos are going to be trying a different way of recording them. That's going to be more based on the PDFs that are shared out so that those will align a bit better. Now, this week's homework is going to be one set of notes. So you'll notice that you have 2.7 here, and this is your first presentation, and then 2.9. So 2.7 is taking general statements and converting them into symbolic logic. And then 2.9 is taking statements that are written with these symbols and interpreting them and determining whether they are true or false statements. So get yourself ready for notes, and we're going to get started. Now, the most important symbolic logic symbols that are new are going to be these ones right here. So I'm going to go through and define what they all mean, and then we'll talk about using them. So this first one here that looks like an upside down A, that means for all. So that just means for every type of number in a set for every element. This backwards E means there exists. So for every element there exists something. This tilde, this little squiggly line, is a way to negate. So this is just a way to say not. We also might use the strike through for like not an element of, not equal. This arrow here means implies. So if this, then this, X implies Y. And then our familiar friend here, which means therefore. So there's, just like when we're writing in English, there's several ways to write statements in symbolic logic. I will go through some. I'm not going to write a bunch for every single example, but if you think that you have one that you're like, I think this works for this example, feel free to reach out, share, ask questions about it if you're not sure. 1. Write in symbolic logic. Given any natural number n, 2n is even. So the first thing before we get started, we're going to say, all right, if you have anything that's, any or for all, that means that you're going to, like this. So if you see the word any or every, that's a sign that you're going to use this symbol. And then we have natural number n, so n in the natural numbers, which would be this. Next section, 2n is even. So you can write out the words even, or you can recall from very early in the book that E is the set of even numbers. And there is a complementary O, which is the set of odd numbers. So you definitely might use some of those in this homework, and you're definitely going to use it going forward in this class. So if we string this all together, the way that we'd write this in symbolic logic is we'd say for every n in the natural numbers, 2n is in the even numbers. And the main thing with symbolic logic is it lets us write with more concision, meaning that we are taking less symbols to say the same thing. Here we have a couple more to practice with. If a set has more than 3 elements, at least one subset of that set also has 3 elements. So again, we will go through and interpret. So here we could say, if a set has more than 3 elements, so the way I would state that is for every set X, and all you need to do is use this capital letter. Capitals mean that it is a set, and then we give it a parameter where the cardinality of X is equal to or greater than 3. We say there exists one subset of X, and you might just put a comma. I also had a lot of professors who would say such that, or they might even abbreviate it as just ST, such that the cardinality of A is equal to 3. Again, this is not the only way to say this. This is one of them. So if I'm looking at how did I know this was how I was going to do it, we have an undefined set, which is a sign that we might want to use the for all. And it has more than 3 elements. Counting elements is cardinality. And then more than 3 gives us our inequality. And if it says something like at least, that is a sign that we might want to use a there exists. Because what that means is that there is one of this thing. There might be 2, there might be 70, but there is at least one. One exists. Another one. Every integer that is not odd is even. So again, we see this word every. So we're going to use the for all integers. So that means we're going to say x, that is an element of z, is an element of the integers. If x is not odd, so we're using our element sign here. You could also, if you want to use the is not an element of the odd numbers, these two mean the same thing, implies, so here we have an if then, so if x is not odd, then x is even. Last one, there is an integer solution. So here, there is the same as saying there exists. So there exists an integer solution, so an integer, such that x squared is equal to 2. We can convert it into symbolic logic. Doesn't make it true, as we've talked about, statements are statements, whether they are true or not. But here's a nice example of how to convert. Now, you can pause here and do the first assignment, or you can keep going and have a full work day tomorrow, because the second assignment is about translating things that are in symbolic logic into plain text. So here we have some statements that are already written in symbolic logic, and we want to decode and decipher what they're saying. Now, if you remember taking classes in Latin and Spanish, you will have something that is an exact translation, and you'll also have a regular translation, something that's just a little bit more easily understood. So what I always recommend is that you start with an exact translation. An exact translation means that we're not going to put any interpretation, we're just going to write what this says. So we see, for every x in the real numbers, there exists a y in the real numbers where y cubed is equal to x. So I'm going to interpret these commas. Sometimes you don't need to add a word. Sometimes you might to make it colloquial. And as you notice, I already did because we're just so used to reading like that. So in this place, just like we talked about in the first part of the lesson, you want to either add a where or a such that, so that you have something that makes sense. And then once we have an exact translation, then we're going to turn it into plain text. So I would maybe start with this first clause. For every x in R, I would say for every real number, because that just sounds more like how we talk, there is another real number. And now here's where we want to interpret this last statement. This other real number cubed equals x, so this number y is the cube root of x. So there exists another real number that is its cubed root. And that would be the interpretation of this complex symbolic logic sentence. Now, if you look at the second example here, these are almost identical, but all that's happened is that the first clause and the second have been reversed. And just like when we're speaking, order matters. This isn't Latin. You can't just reorder things in whatever order you want. It needs to follow a certain flow. And we can tell this because we're going to get a different meaning based on this order. So here we've interpreted it to say there exists a real number that for every other real number, for all x and r, it is its cube root. Same thing. So we have the same symbols, but this obviously went from being a true statement to a false statement. There is no number that is a cube root for everything. So it's really important that you make sure that you're not switching around the clauses when you are doing your translation. Here's our last example where we're using sets. Here, again, we're going to start with an exact translation, which says here, for all x in the power set of n, x is a subset of r. So that would be our exact translation. Now we want to ask ourselves, what does it really mean? So when we start with for all x in the power set of n, that is another way of saying for every subset of the natural numbers, it is a subset of the real numbers. And I think you could probably do an even more direct translation that's even more easily understood that would just say every subset of the natural numbers is also a subset of the real numbers. Please let me know if you have any questions about this. Again, this video spans both lessons. And if you are stuck on anything, please do be in touch, either with making a Zoom appointment in the calendar at the top of the classwork page, or copying and pasting the calendar link from the banner in Google Classroom.